Hello, my name is Ricky Gracia, and I will be presenting the data cleaning portion of Group 7's final project. In today's competitive retail market, companies must leverage their data to improve profitability, optimize pricing strategies, and better understand customer behavior. In this project, we focused on analyzing sales transaction data to support decision-making through predictive modeling and customer segmentation. We used a data set that we found on Kaggle, and we created two analytical models, the unprofitability prediction model and the customer clustering model. The data that we downloaded was pretty clean, and we know that data cleaning is an important step to ensure that predictive and clustering model produce reliable and interpretable sources. So we definitely made sure to clean as much as possible. The data set was imported into RapidMiner, and during import, the attribute types were verified to ensure that numerical variables were correctly recognized as numerical, while categorical variables were identified as nominal. The data was analyzed to identify missing values, inconsistent data types, extreme values and anomalies, and duplicate records. During our data cleaning, we decided to filter out an outlier in sales. We filtered out sales that were less than or equal to 4,000. Filtering outliers helps reduce noise in the data. For the decision tree, additional attributes were generated using the generate attributes operator. So discount buckets were created by grouping discount percentages into ranges, which improved interpretability in the decision tree model. A profitability label, so profitable or unprofitable, was derived from the profit variable and used as the target variable for the classification model. Sales quantity was changed to unit price, order date and ship dates were changed to shipping days. These transformations helped optimize the data set for the decision tree. After cleaning and preparation, the data set was validated using summary statistics and visual inspections to ensure no remaining missing values, consistent attribute formats, and reasonable value distributions. Thank you.
Hello, my name is Gianluca Zigni, and I'll be showing how the two models were created. So we started off by importing our data and then multiplying to have the data split out so we can separate and do the two models independently. I'll start off with the decision tree. So with the decision tree, we started off by filtering as part of the data cleansing, as there were some outliers in the sales for sales above $4,000. Then we generated some attributes. So we generated unprofitability attribute to make sure that we categorize every sale that was not profitable with profit less than or equal to zero, as true or false. Then we calculated the unit price, shipping days as the difference between the ship date and the order date, the discount bucket. So we bucketed the discounts into 0 to 10%, 10 to 20%, 20 to 30, and 30 to 50, and above 50%. So discounting. And we selected attributes. We got rid of everything that wasn't not available at the time of purchase, as that's how in the future the model would apply to orders before they're purchased, and all the costs associated are calculated and the profit is calculated. Then we set the unprofitable attribute, generated attribute, true or false as the label, and then we did a split to do the decision tree model. The decision tree model was created using gain ratio with a max depth of 10, pruning and pre-pruning, the default pruning, pre-pruning, and then a minimum leaf size of 2 and a split of 4. And for performance, we added accuracy, AUC, and precision. For the clustering model, we first multiply the incoming data again, just so we have the data available for later. But we did the aggregation by customers so that we have total sales, total quantity, average discount, average profit, and number of orders by client. We generated some attributes here, the average unit price, and then we normalize all the values. We set the customer ID as the ID, and then we ran clustering with k equals 4, max runs of 300 with divergence of squared Euclidean distance. From here, we selected just the cluster, and then rejoined it with our original data so that we can re-aggregate with the clusters so that we get the average sales, average profit, average discount, and number of orders by cluster. And yeah, and that's how we ended up with the 4 clusters and then all the attributes. And then for the decision tree, this is how our decision tree.
Professor. So I am doing the interpretation for clustering. Um, we chose to do a k-means clustering model, and we applied it to furniture sales data. And we're comparing a global data set of about 2,000 records to a subset of 707, as we can see here. Cluster 0 features 493 items, Cluster 1 features 1 item, Cluster 2 is 3 items, Cluster 3 is 210 items for a total of 707. So, Cluster 0 represents low engagement and infrequent transactions with below average sales. So this cluster is basically netting zero profit. And we can see that here in the negative z-scores. Then we have cluster 1. Cluster 1 is very unusual. I would consider it an outlier just because it has high profit, but almost no transactions, with the transactions being only one every so often. And then we have cluster 2, which causes a huge dip in profits, evidenced by this negative 9 z-score. And then we have the cluster 3, which is the most stable of all 3 clusters. Most of the numbers are in the positive. The only one that's in the negative is the discount, but even then the discount is at a normal rate that people find acceptable enough to buy in volume. We can see that evidenced here a lot more clearly with the graph. Cluster 3 is in red, and it is the most stable amongst all the categories with no highs and lows, while cluster 1 peaks at profit and cluster 2 dips at profit. These extreme highs and lows are not good for business and can put the company not at risk. Cluster 2 will definitely put it at risk, and cluster 1 is great, but cluster 1 is not reliable. So these are not good factors to consider when it comes to discounting. Then we have cluster data here, where we can really see in percentages what would be best. So the average discount for cluster 3 is 50. Oh, I'm sorry, that was incorrect. The average discount for cluster 2 is 53%, cluster 3 is 17%, and cluster 1 with 0%. So with these clusters, we can determine that cluster 3 is the most stable foundation for the company. Cluster 2 is way too detrimental. 53% is way too steep of a discount to yield any profits and actually increases financial risk. While cluster 1, while nice, is not reliable, I would consider it an outlier. It demonstrates that sales can still be made, but given that there's only one every so often, it's not a reliable factor or predictor for how well the company will do with keeping zero discounts. Thank you.
Good evening. My name is Jaden Campbell, and I'll be going over the interpretation for the decision tree method. So, of course, today I'll be discussing how we use the decision tree model to predict unprofitable orders and what insights we gain from it. Decision trees are a powerful yet easy to understand analytical tool. They work by splitting data into branches based on a series of decision rules, which makes it very clear how different variables influence the final outcome. One of the main advantages of decision trees is their interpretability. Instead of being a black box, we can clearly see which factors matter most and why certain predictions are made. And then, of course, in our analysis, we applied a decision tree to determine whether a new order is likely to be unprofitable. The model evaluated several key order and customer characteristics, including discount buckets and product category, quantity, customer segment, unit price, and shipping time. By analyzing these factors together, the model helps identify risky transactions before they are processed, allowing the business to take preventative action and reduce potential losses. In terms of this performance, the model produced strong results. It achieved an overall accuracy of 89.76%, meaning that's nearly 9 out of every 10 orders were classified correctly. This shows that the model is highly reliable overall. And more importantly, the model demonstrated an exceptionally high precision of 98.17% for unprofitable orders. This means that when the model predicts an order will be unprofitable, it is almost always correct. From a business perspective, this is extremely valuable because it minimizes false alarms and ensures that flagged orders truly deserve attention. Also, looking more closely at the results, the confusion matrix further confirms the model's effectiveness. Out of all the orders predicted as unprofitable, 161 were actually unprofitable, while only 3 profitable orders were incorrectly flagged. This indicates a very low error rate when identifying risky orders. Additionally, the model correctly classified 409 profitable orders, although it did miss 62 unprofitable orders, which were predicted as profitable. This leads us to the recall for unprofitable orders is 72.20%, meaning the model successfully captured about 7 out of every 10 loss-making orders. On the other hand, the recall for profitable orders is 99.27%, showing that the model is extremely effective at recognizing profitable transactions. Overall, the model prioritizes precision over recall for unprofitable orders, which is a sensible trade-off when the goal is to avoid unnecessary intervention on profitable sales. Finally, the model achieved an AUC of 0.954 for the positive or unprofitable class. This is very this is a very high AUC value, indicates excellent discriminatory power, and shows that the decision tree is highly effective at separating unprofitable orders from profitable ones across different decision thresholds. And in conclusion, I would say the decision tree provides clear, interpretable insights into the key drivers of unprofitability, such as high discount levels, low unit pricing, order quantities, and longer shipping times. As a result, this model serves as a strong decision support tool for sales and pricing teams, helping them make better informed decisions and ultimately reducing profit losses. Thank you.
Hi, my name is Jacqueline Vasquez, and I'll be presenting you the conclusion portion of our final project. For the conclusion of our project, we compared the two models we used, clustering and the decision tree, to explain what they reveal from a business decision-making perspective and how they work together to inform strategy. We begin with the clustering model, which helped us identify overall transaction patterns by grouping sales into 4 distinct clusters based on sales, quantity, profit, discount levels, and unit price. What became very clear is that not all sales contribute equally to the health of a business. Cluster 3 stood out as the most stable and reliable group. It reflects frequent transactions, moderate discounts, and consistent positive profit, making it the strongest foundation for sustainable revenue. In contrast, Cluster 2 showed the aggressive discounting leads to financial losses despite higher sales volume. And while Cluster 1 demonstrated that high-priced items can be sold without discounts, those transactions occur too infrequently to rely on long-term. The decision tree addressed a different but equally important question by explaining why these outcomes occur. This model clearly showed that the discount level and unit price are the most influential variables driving profitability, followed by quantity sold and customer segment. The tree made it easy for us to see how deep discounts applied to high-priced items quickly result in negative profit, while moderate discounts paired with reasonable pricing and volume lead to more favorable outcomes. One of the strengths of the decision tree is its interpretability as it translates complex data relationships into clear, actionable decision rules. When we compare both models together, the comparison table in this section highlights how they complement each other. The clustering model provides the big picture by identifying stable versus risky sales behavior, while the decision tree explains the specific drivers behind those results. Together, they reinforce the same key insight. Overall, both models lead us to the same conclusion. Sustainable profitability is driven by consistent sales volume and controlled discounting, not by extreme promotions or reliance on rare high-volume transactions. Combined, these models offer a strong foundation for making smarter pricing and discount decisions that support long-term business stability.